Apache Kafka is a popular open-source distributed streaming platform. It seamlessly handles real-time data streaming and processing, ensuring that information flows smoothly and reliably. Kafka is instrumental in event-driven architecture. It serves as a messaging layer in microservices, promoting a scalable and loosely coupled architecture. In this video, we'll explore the diverse applications of Kafka, a widely used open-source streaming processing platform that has revolutionized the way enterprises handle and process data. Throughout the video, we'll delve into the intricate details of Kafka architecture, exploring its key components and their roles in the overall data processing pipeline. We shed lights on topics, partitions, producers, consumers, consumer groups, Kafka clusters, and brokers, explaining how they work together to ensure efficient and reliable data storage and retrieval. One of the key highlights of the video is the demonstration of Kafka capabilities in handling high volume of data streams. We'll walk through practical examples where Kafka ingests and processes millions of events per second, illustrating the scalability and resilience. By the end of this video, you will have a solid understanding of all the basics of Kafka. So, let's get started. Companies often have a source system such as a database which act as a central repository for valuable data. This data is crucial for various business processes and decision making. However, as organizations grow and evolve, the need arises to share and utilize this data across different departments and systems. This is where the concept of data migration comes into play. Data migration involves transferring data from the source system, that is the system where the data originates, to a target system or systems where the data is consumed. The purpose of data migration can be diverse, such as consolidating data from multiple sources, upgrading to a newer systems, or integrating with external systems for a seamless data exchange. Initially, data migration may seem like a straightforward process. It may involve writing code to extract data from the source system, transform it to fit the requirements of the target system, and finally load it into a target system. But as your business grows and evolves, you may find yourself with multiple source systems and multiple target systems. This can significantly complicate data integration challenges as each source system must communicate with each target systems to share information. So previously, if you had 4 source systems and 4 target systems, you would need to create 16 integration points to make everything work. Each integration involves several complexities, such as protocol differences, that is, data can be transmitted over TCP, HTTP, REST, FTP, JDBC, etc. Or the data format concerns, that is, the data itself can be binary or CSV, JSON, Avro, or protobuf, etc. Additionally, each source system experiences increased load due to the numerous connections and requests for data extraction. So basically, data integration presents various challenges when dealing with multiple source and target systems. Ensuring data consistency, maintaining data quality, and protecting data security, and achieving efficiency and scalability are key challenges. Apache Kafka addresses some of these issues by offering a scalable, reliable, and real-time data streaming platform that addresses these challenges head-on. Apache Kafka was initially conceived by LinkedIn as an open-source project and is currently primarily maintained by a consortium of notable corporations, including Confluent, IBM, Cloudera, and LinkedIn itself. Kafka's robust distributed architecture, coupled with the fault tolerance, allows for system upgrades and maintenance without disrupting operations. To understand and appreciate the power of Kafka, we first need to understand the basics of messaging, which I have explained in my previous videos in detail, where I have talked in depth about peer-to-peer and pub-sub patterns, explaining their limitations, advantages, and uses with examples. In essence, messaging involves sending a message from one location to another. It has 3 components. A producer, which is the entity responsible for creating and sending messages to one or more queues. A queue, which is a buffer data structure that receives messages from producers and delivers them to consumers in a first-in, first-out manner. Once a message is delivered, it is permanently removed from the queue, eliminating the possibility of retrieving it later. The consumer is the entity subscribed to one or more queues, receiving messages when they are published. Now that we know how messaging works, let's dive into Kafka world. At the core of Apache Kafka lies a publish-subscribe architecture. Producers are data publishers. They publish data to designated topics, while consumers are data subscribers who eagerly sign up for those same topics. This decoupling creates a highly scalable and manageable environment for data integration pipelines. Let's break down these fundamentals, starting with the concept of topics, partitions, and offsets. Kafka operates within a cluster. Think of Kafka cluster as a group of computers or servers working together as a single system. This cluster is what provides the power and reliability to handle massive amounts of data flowing through your topics. Kafka topics are designed to handle continuous streams of incoming data. It's like a river of information constantly flowing through your Kafka system. Each topic represents a specific category of this data flow. Imagine you are running a hot new social media app. People are constantly posting updates and you need a system to handle this constant data flow. You could have a post topic for all those amazing user updates, a likes topic for every time someone shows some love, and maybe even a follows topic to track the connections between users. Just like different hashtags categorize posts on social media, topics categorize your data streams in Kafka. Think of topics like tables in a database, but without the rigid constraints. Unlike traditional databases with strict data types and schemas, Kafka topics are much more flexible. You can send any type of data you want to a Kafka topic. You can throw in a JSON data, text, images, anything. This makes Kafka well suited for handling the varied data formats common in modern applications. Kafka isn't meant for permanent storage. Data is kept for certain duration, usually a week by default, and then it is automatically cleaned up. This ensures Kafka focuses on processing real-time data rather than being a historical archive. Kafka topics are also immutable, which means that once data is written, it becomes a permanent record. You can't go back and edit or delete individual messages. And this is different from a database where you can update rows. Understanding immutability and data retention is crucial for designing systems on top of Kafka. Since data can't be changed, Kafka encourages event-driven architecture, that is, systems that react to events as they happen. Think real-time analytics or triggering notifications based on user actions. I will talk more on these concepts in my future videos, so stay tuned. Now, these topics can get pretty busy. To handle the high volume, Kafka slices each topic into smaller chunks called partitions. Imagine each topic as a highway with multiple lanes. These partitions are those lanes allowing for faster processing of the data stream. You can even have as many partitions as needed depending on the amount of data flowing through your topic. Each message is assigned to a specific partition. Messages within a partitions are ordered, meaning they will be processed in the order they were received. The sequence of messages in a topic is called a data stream, and this is why Kafka is called a data streaming platform. Every single message that zips through a partition gets a unique ID called an offset. It is like a serial number assigned to each message in the order it arrives. This keeps things organized within each partition. Think of it like a queue. The first message gets offset 0, the second message gets offset 1, and so on and so forth. It is a unique ever-increasing number. This way, you can always track the exact position of a message within the partition. If something crashes, you can restart reading from the last processed message, avoiding duplicates or missed data. So offsets ensure messages within a partitions are processed in the exact order they arrived. Without them, it would be a chaos. So when a user posts something, the update gets published to the post topic. Kafka might automatically distribute the messages across one of the partitions within the post topic. Within that partition, the messages gets assigned an offset based on its arrival order. Now, other parts of your system acting as consumers can read and process these messages. Maybe one consumer analyzes the sentiment of post, while another pushes them into the newsfeed. The key points to remember are, once data is written to Kafka, it's like writing in ink. You can't change or delete it. Kafka keeps your data for a specific period before deleting it. Messages within a partitions are processed in the order they arrived based on their offsets, but there is no guaranteed order across different partitions. And finally, by default, messages are placed into partitions randomly for load balancing. However, you can also specify a key to ensure related messages end up in the same partition. Now, say our social media app is buzzing with posts, likes, and new connections. Kafka producers take the center stage here. Producers are the parts of your app that create and publish these messages. For every person posting an awesome photo, there's a producer saying, "Hey Kafka, store this photo." For every like button clicked, there's a producer sending a small message into the likes topic. Producers don't just send data randomly. They know which topic it belongs to and even which partition within that topic. Just like you decide where your social media content goes, general feed or a specific hashtag based topic, producers make similar calls. Sometimes a message will have a special key attached. Maybe it's the user ID or a hashtag for the post. This key guarantees that all messages within the same key end up in the same partition within the topic. This is how we've maintained order for specific things, like making sure one user's post end up in the right. If there is no key, the message gets set out round robin style between partitions. This helps in load balancing the workload across your Kafka cluster, so no single partition gets overwhelmed. For example, when you're posting in your social media app, let's say a user posts a hilarious meme. Here is what the producer might do. The producer bundles the meme image, some text, and the user ID into a Kafka message. The user ID acts as the key. The producer then picks up the post topic, and because we have a key, it figures out the correct partition based on the user's ID. And finally, the message zooms off to the right partition and gets assigned its offset. But there is one crucial step before sending: serialization. Kafka deals in bytes, the raw building blocks of computer data. Your messages, though might be complex objects like user profiles or image data, serialization translates these objects into a byte format Kafka can understand and store. During message construction, when the producer creates a message containing the meme image data, a caption, and the user ID, here is where the chosen serializer comes in. Maybe we are using a JSON serializer. This takes the entire message, which is the meme image, data, caption, and the user ID, and transforms it into a stream of bytes, essentially a JSON representation in byte format. So now the producer has a message Kafka can handle, and it sends the serialized message to the appropriate partition in the post topic. Kafka comes with several built-in serializers for common data formats like string, integers, and JSON. You can even plug in custom serializers if you have unique data types in your app. Now, producers are the parts of your app that create and publish these messages. We need another side to complete the picture. That is where Kafka consumers come in. Consumers are the parts of your app that read and process the data from Kafka topics. So for every like, every comment, every new post, you might have consumers doing different jobs. Consumers subscribe to specific topics they are interested in. Maybe one consumer analyzes posts for trending hashtags, while another sends out this cute, your friend liked this notification. Consumers also read and process, and here is where the magic happens. Consumers fetch messages from their assigned partition in the order they arrived. Remember those handy offsets? But wait, Kafka deals in bytes, and our app needs usable data. This is where deserialization comes in. The consumer uses a deserializer. This is the flip side of the serializer we saw with the producers, to turn those bytes back into human readable form like JSON or plain text. Imagine this process as unwrapping the message from Kafka, and once deserialized, the consumer can get to work on the actual data, updating a real-time trend chart, triggering notifications, or anything else your application needs. Consumers track their own progress within partitions. This way, if there is a hiccup and a consumer needs to restart, they know exactly where they left off and can avoid missing on reprocessing data. Often, you'll have multiple instances of consumers working together to handle the load. This is a Kafka consumer group. It's like having a team tackle a giant newsfeed. Within a consumer group, each consumer gets assigned a chunk of the partition from a topic, and this helps to balance the workload and handle a high volume of data. If one consumer in the group goes down, its work is seamlessly reassigned to others. This ensures your data is always being processed without missing a beat. While you can have several independent consumer instances to handle the giant newsfeed, consumer groups offer several key advantages. Without consumer groups, if you have multiple instances reading from the same topic, they'll all receive and process the same messages. This leads to duplicate work and potential issues. For example, imagine multiple instances trying to send the news to a user. Within a consumer group, each partition gets assigned to only one consumer instance. This guarantees that every message in a partition is processed by exactly one member of the group. So, when a consumer group contains just one consumer, it will get all messages from all partitions in the Kafka topic. When a consumer group contains two consumers, each consumer in the group will be assigned to half the partitions in the topic. The consumer group will continue to balance consumers to partitions until the number of consumers is the same as partitions. Once there are more consumers than partitions, the excess consumers will sit idle and receive no messages. This means the number of partitions in the topic will be the limit on the effective number of consumers that consume messages at any given time. You can also have multiple consumer groups reading from the same topic. Each consumer group will maintain its new set of offsets and receive messages independently from the consumer groups on the same topic. To say it simply, a message received by consumer group 1 will also be received by consumer group 2. Within a single consumer group, a consumer will not receive the same messages as other consumers in the same consumer group. Each consumer group is identified by a group ID. It must be unique for each group. That is, two consumers that have different group IDs will not be in the same group. So in our social media app, you could have a consumer group dedicated to monitoring post topics that can provide valuable insights into what's trending in a social media. By analyzing a portion of the post, these consumers can identify trending hashtags and update a live dashboard accordingly. This information can help businesses stay informed about the latest trend and tailor their content to resonate with their audience. A separate consumer group focused on the likes topic can handle sending out real-time notifications whenever someone likes your content. This feature can be particularly useful for businesses looking to engage with their audience and build relationships with potential customers. By promptly acknowledging likes, businesses can show their appreciation and encourage further interaction. Another potential consumer group could be responsible for sentiment analysis. These consumers would analyze the sentiment of posts and comments related to your brand or a specific topic. This information can provide businesses with valuable insights into how their brand is being perceived and can help them adjust the marketing strategy accordingly. After you start to read a bit more about Kafka consumers and start configuring your own consumers, you will see the term offset and commit more and more. Apache Kafka does not have an explicit way of tracking which messages has been read by a consumer of a group. Instead, it allows consumers to track the offset, that is the position in the queue, of what messages it has read for a given partition in a topic. To do this, once in a while, consumer in consumer group will publish a special message topic for the topic or partition with the committed offset for each partition it has gotten up to. Apache Kafka stores consumer offset in a special internal topic called consumer offsets. So when a new consumer is added to a consumer group, it will start consuming messages from partitions previously assigned to another consumer. It will generally pick up from the most recently committed offset. If a consumer leaves or crashes, the partition it used to consume will be picked up by one of the consumers that is still in the consumer group. This change in partitions can also occur when a topic gets modified or more partitions are added to the topic. The process of changing which consumer is assigned to what partition is also called rebalancing. Rebalances are normal part of Apache Kafka operations and will occur during configuration changes, scaling, or if a broker or consumer crashes. Generally, you want to avoid rebalance if you care about real-time consumptions of messages, as some messages cannot be read during rebalance, which results in loss of availability. It's important to note that Kafka consumers pull data from the topic they are listening to. This allows different consumers to consume messages at different rates without the broker or Kafka having to determine the right data rate for each consumer. It also allows better batch processing mechanics. Luckily, the Kafka Consumer API also allows client applications to treat the semantics as push if you wish. For example, you get a message as soon as it is ready, without the need to worry about the client getting overwhelmed. When it comes to delivering messages in Kafka, there are few key guarantees or semantics that you can choose from. The semantics define how Kafka ensures messages that get delivered from producers to consumers. So in our social media app, for instance, delivery semantics determine how reliably these likes and posts get sent and processed. At most, one's delivery prioritizes speed above all else. Messages might be delivered once, but there is a possibility of losing messages entirely if there are failures. The key here is that the consumers will never receive duplicates. For example, a user scrolls quickly through their feed, generating seen events. At most once might be okay here, as losing a few seen events is likely not a big deal. At least once delivery is the most commonly used option in Kafka. It offers a strong guarantee. A message will be delivered one or more times to its consumers. This means you can be sure your messages won't be lost entirely, but there's a chance you might see duplicates. Exactly once delivery strives for a perfect balance. Each message is guaranteed to be delivered only once to each consumer. This is ideal for scenarios where duplicates are absolutely critical, like financial transactions. However, achieving exactly one semantics requires more complex configurations and can introduce some performance overhead. Imagine a user credits your social media app with $1 to buy coins for an in-app purchase. Exactly once delivery would ensure this critical financial transaction is only recorded once in your system, preventing duplicate charges. The best delivery semantics for your application depend on specific needs. If you can tolerate duplicates and prioritize speed and throughput, at least once is a strong option. If ensuring zero duplicates is vital, exactly once delivery may be the way to go, even if it means some trade-offs in performance. Earlier, we learned that a Kafka cluster isn't just one machine. It's a powerful distributed system made by multiple servers called brokers. These brokers work together to provide a highly available and scalable platform for handling real-time data streams. Each broker stores a portion of their data and is responsible for processing requests from producers and consumers. They receive data from producers and send it out to consumers. Brokers act as the receiving point for messages from producers, ensuring they are safely stored and replicated for fault tolerance. Brokers efficiently store messages published by the producers within the topic partitions assigned to them. Brokers manage consumer subscriptions and deliver messages to the appropriate consumers based on their subscriptions and offsets. And for reliability, Kafka replicates each partition across multiple brokers in the cluster. This means there are copies of the data on different servers. If a broker fails, another broker with a replica can take over and continue serving messages, ensuring minimal disruptions to data access. Imagine a large library with many books. A single librarian managing all these books would be overwhelmed. Similarly, a single broker wouldn't be able to handle massive data efficiently. That is why Kafka topics are divided into smaller, more manageable units called partitions. These partitions are then distributed across the brokers in your cluster. This distribution strategy has two main benefits: scalability and parallel processing. So if your data keeps growing, you can simply add more brokers to the cluster. Each new broker can take on some of the data storage and processing load, keeping your system running smoothly. Consumers can read data from multiple partitions simultaneously across different brokers. This parallelism allows Kafka to process large volumes of data much faster than if everything was stored on a single server. One of Kafka's key strengths is the horizontal scalability. It enables you to add brokers over time to your Kafka cluster, allowing you to scale to hundreds of brokers and handle massive amounts of messages throughputs of millions of messages per second. The scalability makes it well suited for large-scale applications such as Twitter, where real-time data processing is critical. The image here illustrates the basic building blocks of how Kafka stores and manages streams of data ready for sending and receiving by applications. It illustrates the relationships between topics, consumers, partitions, and other concepts like replicas, brokers, producers, etc. Take a moment, pause the video to revise and understand their relationships better. Apache Kafka applications are as diverse as the organizations that use it. It's a highly scalable messaging system for distributed systems, facilitating real-time analytics, metric collection, log aggregation, and stream processing. Kafka's popularity is evident with over 2,000 firms and 80% of the Fortune 100 companies using it. Netflix relies on Kafka to power its real-time recommendation engine, delivering personalized movie and TV show suggestions to users. Uber leverages Kafka to track user activities and provide real-time ride updates, ensuring a smooth and seamless ride experience. LinkedIn collects and analyzes user interactions through Kafka to gain valuable insights into its member behavior. Airbnb processes reservation data and manages property listings using Kafka, enabling efficient booking and property management, while Walmart monitors inventory levels and optimizes its supply chain with the help of Kafka, ensuring efficient inventory management and customer satisfaction. In essence, Apache Kafka acts as the backbone of modern data integration, enabling organizations to unlock the full potential of their data, drive innovation, and achieve business success. With that, we have covered the foundation of Kafka. And if you are ready to take it to the next level, get set for a deep dive in my next video.